This lecture is going to look at section 1.4 out of the book, and specifically at the matrix equation AX equals B. First, we're going to look at matrix multiplication. Now, you may have seen matrix multiplication before, but this may be a slightly different way of thinking about matrix multiplication. We're looking at the product of a matrix and a vector. So we are looking at an m by n matrix. M by n matrix means you have m columns and m rows and n columns. And we're going to multiply that by an n by 1 vector. An n by 1 vector has n rows all in one column. When we talk about the product of a matrix times a vector, the product, we think of it as the linear combination. Now we saw what linear combinations were. A linear combination of the columns of A using the corresponding entries in V as weights and is given by that formula where VI are the entries in V, AI are the columns of A. Okay, so let's take a couple of examples and see what we mean by this. And this, as I said, this might be a slightly different way of thinking about matrix vector multiplication than you've seen in the past. So take this first example. This is a 3 by 2 matrix times a 2 by 1 vector. What we're doing is we have, if you look at the formula, we are taking the entries of V and multiplying them by the columns of A. So we take the first entry of V, number 2, times the first column, 1, -4, 3, plus the second entry of V times the second column of A, 4, 0, 2. And notice what we have now. This is a linear combination of the columns of A. It's a linear product. So now we know how to do these multiples. So we can take a number times that first vector, gives me 2, -8, 6, plus the second one is -1 times the second vector, -4, 0, 2. And now we add them up. We get -2, -8, and 8. Oops, that's a -2. And that's not 8, that is 4. -2, -8, and 4. Okay, so that is the matrix vector multiplication. What about the second one? The second one, we have a 3 by 3 matrix times a 3 by 1 vector. We do the same thing. Here we just have some variables, so we just work the variables in. So the first one is the first entry times the first column plus the second entry in my vector times the second column plus the third entry in my vector times the third column. Add those all up, and of course, because we have variables in here, we can't come up with a final number for each. We leave it as equations with the variables. 2x plus 4y, and then 0z. The second entry is 4x minus y plus z, and the third entry is -x plus 2y minus z. And again, this might be a slightly different way of thinking about matrix multiplication. It turns up a matrix multiplication into a linear combination, a linear equation. So that leads us to Theorem 3, which pulls some of these things together. Theorem 3 says that if you have a matrix times a vector equals a column of numbers. So A times X equals B. A matrix of numbers times a column of variables equals a column of numbers. The solution to that is the same as if you write it out in a linear equation, a vector equation. The first variable times the first column plus the second variable times the second column and so on equals that column of constants on the right-hand side. That's going to give you the same result. Which is going to give you the same result as a solution set to the system of linear equations represented by your augmented matrix. So this is pulling together the ideas that we've seen so far and basically formalizing the idea that you can take your equations, turn them into a matrix, solve that augmented matrix, and the solutions you're going to get are going to be the same thing. So now let's see this in practice a little bit, this theorem. This theorem is basically saying that if you want to solve a system of linear equations, that you can turn it into the matrix and your augmented matrix and solve for your augmented matrix in the way we saw last lecture. One of the questions we often ask is there a solution to this system of linear equations? So let's look at an example of this. So we're looking for a solution to ax equals b if and only if b is a linear combination of the columns of A. So in other words, a solution exists if and only if you could take the columns of your matrix, somehow combine them, and get B. So here's an example. We have a system of linear equations, and we're asking, for these values on the right-hand side, can I put anything I want in there and come out with a solution? Or are there some numbers of B that I can put in there that will not have a solution? And this is a common question that you might see asked. Is this system of linear equations consistent for anything, or are there only certain values on the right-hand side for which it's consistent? Well, let's see how we do this. The theorem says that if we have a system of linear equations like this, we can take it, convert it into a matrix form, and then solve for the matrix form. So what happens for this? Here's our equations. So when we have these equations, let's start by putting it into the augmented matrix form. So the augmented matrix form looks like this. 1, 2, 2, so the x column, the y column, and the z column. Oh, that's a 0, and 2z. And then the augmented column, well, in this case, we don't have actual numbers, but we have our variables that represent numbers, b1, b2, and b3. And we're asked, can we put anything into that b1, b2, and b3 and have it come out as with a solution? So what do? We row reduce to get to echelon form. So let's try to bring this down to echelon form. Let's start by noting that we have our first pivot point here. So we're going to turn everything underneath that into a 0. So if we do 2 row 1 minus row 2 is the new row 2, we end up with 1, 1, 1, b1. And now for the second one, we end up with 0, -1, 2, and for the final column, 2b1 minus b2. Then we have 2, 0, 2, and b3. So there's our first operation. Now we're still working with that pivot point. We have another number below there to bring to 0. So how do we do that? Well, 2 row 1 minus row 3 is going to give us our new row 3. So it's 1, 1, 1, b1, 0, -1, 2, and 2b1 minus b2. And for the last row, we get 0, 2, 0, and 2b1 minus b3. So that takes care of that. Now following through with our Gaussian method, we are going to now look at, we've taken care of that pivot column, pivot point, so we're going to take care of this one. So now we are going to do, we need to get rid of the number underneath it. So we are going to do 2 row 2 plus row 3 is the new row 3. So row 1 stays the same, row 2 stays the same, and row 3 becomes 0, 0, 4, and then twice row 2 plus row 3 is going to give us 6b1 minus 2b2 plus b3. So there we go. We are now in echelon form for our matrix. Now with the Gaussian method, we continue on by turning all of the leading entries into ones. So we already have a 1 for the first one. The second and third leading entries need to be turned into ones. I'm going to save a little bit of time and do them both together. I'm going to say negative row 2 is the new row 2, and I'm going to do 1/4 of row 3 is the new row 3. So I'm going to do two operations kind of in one step here, just to save a little bit of time and space. 0, 1, negative 2 b1 plus b2, and we get 0, 0, 1, and 2/3 b1 minus 1/2 b2 plus 1/4 b3. Okay. Now the equations are going to get a little bit more complex, but what we want to do now is we want to take the leading entries and turn the numbers above them into zeros. So the first one is already taken care of. The second one, we have to get rid of something above it. So it is going to be row 1 minus row 2 is the new row 1. And we get 1, 0, 3. And let's see, row 1 minus row 2 is b1 plus, oops, sorry, that's going to be b1 plus 2b1. So it becomes 3b1 minus b2. You get 0, 1, negative 2, and negative 2b1 plus b2. And the third one stays the same as well. 2/3 b1 minus 1/2 b2 plus 1/4 b3. All right, so we've taken care of our first two pivot points. Now we need to take care of our third pivot point, which again, the constant column is going to get a little complex, but let's take care of that. So if we take row 1 minus 3 times row 3 is the new row 1, we are going to get 1, 0, 0. Row 1 minus 3 times the third one, that's going to be 3b1 minus 2b1, so b1 minus 3 plus 3 over 2, that becomes minus 3 over 2 b2, and then minus 3 over 4 b3. There's our first row. 0, 1, negative 2, and this one stays the same, and our final one stays the same. Okay, so now we just have one entry left to get. We have one more non-zero number above our third pivot row. So we are going to do row 2 minus 2 row 3 is the new row 2. And what do we get? The first row stays the same. The second one becomes 0, 1, 0. And row 2 minus 2 row 3 becomes minus 2 minus 4 over 3. So minus 6 over 3 minus 4 over 3. That becomes minus 10 over 3 B1. The B2 is B2 plus B2, so it's plus 2 B2. And then it's minus 1/2 B3. And the final row stays the same. So what do we have now? We have x equals that equation, y equals that equation on the right, and z equals that equation on the right. And you'll see, no matter what you have for B1, B2, and B3, there is always going to be a solution. So there is always a solution for B1, B2, and B3. In other words, the set of equations is always consistent for any values of B1, B2, and B3. Now, this worked it out in excruciating detail. I went all the way to the end until we had a system that is in row reduced echelon form. The reality is, at this point up here, when I got my equations into reduced echelon form, that was enough for me to say, yes, there is a solution. And we're going to delve into that a little bit more in future. But the key point here is that no matter what you choose for B1, B2, and B3, this series of calculations shows that there is always a solution. In other words, the system of linear equations is always consistent. So this leads us to theorem 4, which sums up some of the stuff that we've seen. If we have A being an m by n matrix, then the following statements are logically equivalent. Now, what do I mean by this? When we say that they're logically equivalent, what this means is that either all of these statements are true for a given A, or they're all false. You can't pick that some are true and some are false. It means that the 4 statements are essentially the same thing. That if one of them is true, then they're all true. So what are the statements? For each B in Rm, so in other words, if B is an m-dimensional or an m by 1 matrix, the equation Ax equals B has a solution. So if it's the case that no matter what you pick for B, there is a solution, then it also means that that B is a linear combination of the columns of A. And that's looking at what we just looked at, and the idea of the product of a matrix times a vector. That also means that the columns of A span Rm. So remember what span means. Span means everything you can build from a linear combination of the columns. To say that it spans Rn means that you can get every possible entry in Rm, every possible m by 1 vector you can get by combining the columns of A in a certain way. Equivalently, there is a pivot position for every row of A. So remember in the last one where I said that we really only had to go as far as finding a pivot position in every row? That's highlighted here. We went farther, but you didn't have to. These 4 statements all mean the same thing. Now this is a very important concept because we've pulled together all of the ideas that we've seen so far, and we've said, you know what, these things are actually the same thing. So it's a good idea to get comfortable with this, kind of understand a little bit better how this works, try some of the examples in the book similar to one of the examples that we just saw. And note that for this theorem, when we talk about A, we're talking about the coefficient matrix, not the augmented matrix. Okay? So we're talking about the matrix of the coefficients from your equations, not your constant column on the right-hand side. Okay, so now we're going to think a little bit more about the nuts and bolts of computing a matrix times a vector. I talked about how a matrix times a vector is really doing a linear combination of the columns of the vector, or of the matrix, using the numbers in the vector as weights. We're going to look at it slightly differently here for when you're doing the computations of AX. And we have something called the row vector rule for computing that product. That if the product is defined, then the ith entry in AX is the sum of the products of the corresponding entries from the row of A, and from the vector X. What does that mean? Well, here's an example. We have a 2 by 3 matrix times a 3 by 1 vector. Now, if you think about this for a second, what are you going to end up with? You are going to end up with a 2 by 1 vector. If you don't see why you get that, think about it for a second. That what you end up with is a linear combination of the columns of A. What's the column of A? A column of A is a 2 by 1 vector. So we're going to end up with a 2 by 1 vector. But now what this row vector rule is saying is that if you want to find a specific entry in that result, there's another way of doing it rather than adding up everything. So let's say we want to find this first one. We want to find this first entry. What can we do? Well, this rule says that the first entry is the sum of the product of the first row and the column of X. So in other words, we have the first row, and we don't really care what we have underneath, times 1 to negative 1 equals. We're looking for a 2 by 1, and we're really only asking about what's the first number here. Well, if you only want that number, you just have to take the first row of A times the column. So the first row of A is 1 times 1 plus the second entry in the first row times the second entry in the vector plus the third entry in the row times the third entry in the vector. And then you have something underneath. But again, we're not worried about what's underneath. We're just worried about that first entry. Add those all up. What do you get? A little more room here. So that's 1 plus 2 plus 1 and something underneath. So you know your result is going to be 4 and something underneath. So this is a way of getting a specific entry in your vector. What if instead you want this second one? Well, you do the same thing. You have 3 numbers on top that we don't care about. We're looking for the second entry, so we only care about the second row. 2, 3, negative 1 times our vector. What does that give us? Well, again, we don't care about the top row this time. We're only asking about the second row. It gives us the first entry times the first entry plus the second entry in the row times the second entry in the vector plus the third entry in the row times the third entry in the vector. So this gives us something on top. The second entry is 2 plus 6 minus 1, which gives us 8 minus 1 is something on top, and then a 7. So what does this mean? This means that overall, when we do the multiplication, the overall answer to this is going to be a 4 on top and a 7. But sometimes you don't need the entire result, especially with large matrices, depending on the problem you have. Sometimes you only need a specific number out of your result. This rule gives you a way of finding that specific number without having to do the whole thing. So now this leads us to Theorem 5. So for Theorem 5, looks at distribution rules. In other words, what happens when you start to combine multiplication and addition in matrix vector multiplication, and how can you break things up or combine them? So A is an m by n matrix. U and V are two different vectors, or two vectors in our n, so n-dimensional vectors. And C is a scalar, or a number. The first rule says that if you have a matrix times two vectors added together, you can add the vectors together and then multiply, or you can multiply each of the vectors individually by the matrix and then add. So you can multiply first and then add, or you can add first and then multiply. The second rule says that if you have a matrix times a vector, a scalar times a vector, well, you can multiply the scalar times the vector first and then multiply it by the matrix, or you can multiply the matrix by your vector and then multiply by your scalar. So let's look at a couple of examples of what this looks like. If you want specific proofs of Theorem 4 and 5, they're in the textbook. We aren't going to go over them in this lecture, but here's an example of what I mean by this. Say that your matrix A is equal to some matrix, let's say a 2 by 3 matrix. And we want to multiply that by the sum of a couple of vectors. Okay, so if we want to get this, we can add together the vectors and then multiply. You add together the vectors, you get a 3 by 1 vector, then you can multiply. Theorem 1 says, well, you can actually break this up. This is equal to your matrix times your first vector plus your matrix times your second vector. You can solve these out and you're going to come up with the same answer either way. So give this a try just to prove it to yourself. Do it this way first. Add your vectors together and then multiply. And then do it again, where you multiply your first vector by your matrix, you multiply your second vector by your matrix, and then add them together. And you're going to see you come up with the exact same thing. That's what the first statement here says. The second statement is a similar thing using scalars. So for instance, it's something like our same matrix here times the number 3 times a vector. So if you want to solve that out, you can multiply 3 times your vector, you get 3, negative 3, 12, and then multiply that by your matrix. This second statement in the theorem says, well, you can essentially take this constant and move it outside, and instead do your matrix multiplication first. And you'll come up with the same thing. Again, try this out. Multiply your vector by your constant first, and then multiply by the matrix, and then do it again the other way. Multiply your matrix by your vector, and then multiply by the constant. And you'll see you come out with the exact same thing. Now, an important thing to note here, and we're going to get into this a little bit more, when you are multiplying matrices, the order matters. You have your matrix A is on the left side of your vector. That is very important. And we'll get into this in later lectures. But when you're multiplying matrices or vectors, you never change the order. When you're multiplying numbers, just regular numbers, you know that 3 times 2 is equal to 2 times 3. It doesn't matter what order you put them in. When it comes to matrices, that is very important. You cannot change the order. So you'll notice when I rewrote things, I always write the matrix times the vector on the right hand, the matrix on the left, the vector on the right hand side. Be careful of that. Thank you for your attention. For section 1.4, looking at the matrix equation, AX equals B.